Good afternoon, everybody. Apologies for a small delay due to technical problem in setting up connections. I'll be short in introducing Giorgio Margaritondo. Also because I have the CV here, it's so long, they will take the entire time allocated to the presentation to go through all the achievements and research, and also non-research achievements of Giorgio. Just one thing, Giorgio is a physicist, and today he's going to be talking about the magic of X-ray, simple picture of synchrotrons and free electron lasers. I think it's a great pleasure to have Giorgio here giving this talk. Also, by the way, Giorgio is the president of our scientific and technical committee, has been serving IIT for many years, and has been helping in building what is IIT today. So a big thank you, Giorgio, for taking this role and helping us in structuring IIT. So the floor is yours, and as in the other talks, people can pose questions through the chat, and I'll be passing the questions to Giorgio later.
Okay, thank you very much. First of all, let me check about the connections because we had this small problem. So can you listen to me? Can you hear my voice?
Yes.
Okay. Yes. Second, I'll start the presentation now. No. Okay. All right. What I want to talk about today is this gigantic enterprise that is going on all over the world about the production and use of X-rays. And I will talk about synchrotron radiation. I will also talk about free electron lasers. Now, before starting, let me mention a little bit about what you can do with this kind of radiation. Well, I mean, I cannot avoid talking about COVID in these days. And indeed, the CERN Courier has mentioned synchrotrons and free electron lasers as the front line of coronavirus. But to me, even more impressive is the overall picture. You can see here that this is now a gigantic enterprise all over the world with huge investments, and above all, with tens of thousands of scientists that are using these machines. And so, in many cases, the description of these machines is very complicated. I would like to show you that there is no need to be so complicated, and hopefully at the end of this hour, you will have a simple picture of how the machines are working and a little bit what you can do with them, okay? Now, before launching the scientific description, I think it is important also to give some motivation. Why are these 60,000 plus scientists interested in X-rays? I think you can rephrase the question by asking, what you find in nature that has a size, either a physical size, that is the wavelength, or an energy size, that is the photon energy, that is commensurate to X-rays. And let's have a look at the electromagnetic spectrum. You can see here X-rays at the end of the spectrum. If you zoom, then you find that these are the wavelengths, and these are the photon energies. So what you find in nature in these ranges? First of all, the wavelengths. It's very simple. We are talking about angstroms. And so it is the length of chemical bonds and all things associated to chemical bonds. From the energy point of view, you find the energies of electrons that are either directly or indirectly involved in the formation of chemical bonds. So you can summarize these discoveries by saying that X-rays are important because they are the ideal probes of chemical bonds. And if you stop for just a moment and look what you're doing, you find that in 99% or more of science and technology, deep down, what is there is the formation and properties of chemical bonds. So X-rays are not a niche instrument, they are a universal tool to study one of the most important aspects of science and technology. I hope that this is giving the motivation. And now let me go then into the fact that we would like to have good sources of X-rays for research. And we are immediately getting into, first of all, a huge problem and then a paradox. What is the huge problem? What is the paradox? So now let me start from the emission of radiation in a completely different part of the spectrum. Here we are not talking about X-rays, we are talking about radio waves. Radio waves is a wavelength that may be on the order of 1 meter. And you can see that the size of the source is not very much different from the wavelength you emit. And so you can imagine some kind of scaling law whereby when you go to the wavelength of X-rays, which are much, much smaller, on the order of angstroms, you must go down in size. So the source is decreasing and you're getting X-rays. Now, this is not a crazy idea after all, because if you analyze the conventional source of X-rays, those that you find, for example, in a medical cabinet, can easily realize that what really emits are indeed the atoms in the device. But there is a problem, that is the sources of X-rays for medical applications are very, very bad. And you can understand that because if you walk into a medical cabinet for X-rays, you find that everyone is trying to protect himself or herself from the radiation, because the radiation does not go only where it is useful, but it goes everywhere. And furthermore, it is very weak to start with. So this is not a good source for research applications. You like to get something better, but then we are stumbling into the huge problem because according to our scaling law, we should start building artificial devices with the size of a couple of atoms. No way, this is mission impossible. And so we are hitting a roadblock. Now, having presented a huge problem, let me go to the paradox. The paradox is that in spite of this apparent impossibility, we have been using excellent artificial sources of X-rays for very many decades. And that is a picture of one that is very dear to me. That is Electra in Trieste. I was for a while the scientific director of this machine. And it doesn't look to me like something of the size of a couple of atoms. We're talking about a couple of kilometers here. So there is something that is paradoxical. There is something that does not work with our scaling law. How can we reconcile these two aspects? Okay, we are getting now into the basic message of all my presentation. And the basic message is that it is our good friend Albert Einstein that is teaching us how you can start from huge things like Electra, you can shrink them down with relativity and be able to emit microscopic wavelengths. So let's start discovering how Albert Einstein is teaching us to do that. We'll start from classical physics. If you want to emit radiation, for example, X-rays, that are electromagnetic waves, you must have an electric charge and you must have an acceleration of the electric charge. I would propose to use electrons because they are charged, but also they have a small mass, so they are easy to accelerate. And let's be concrete. Let me propose a device. Here we have an electron that is going at slow speed into a series of magnets, what we call in an undulator. Okay, to see what's happening, let's take a top view here, and you can see the electron getting into the undulator, and because of the magnets is going to oscillate in the transverse direction. Because of the oscillations and the acceleration, you get electromagnetic radiation, and so we are in business. Well, we are almost in business, because the question is, what is the wavelength that you are going to emit in this way? And that's not good, because you can easily realize that the wavelength must be related to the period of the undulator, but the period is going to be something of the order of centimeters or millimeters perhaps, which is way too large for X-rays. We're talking about something which is more in the microwave range for your kitchen. And so there is something that we must do in order to get to X-rays, and this is relativity. So let's take the same device, but this time, instead of taking a slow speed electron, let me take a high speed electron. Now, there is a good way to handle relativity, and this is to start changing the point of view that is the reference frame. And let me propose to you to take the reference frame of the electron. Now, the electron here sees the undulator as coming at a speed close to the speed of light. So that is one effect, but it is not the most important. The most important is that in relativity, when you have an object and the object is moving, then the length of the object decreases because of a phenomenon that is called the Lorentz contraction. So the undulator looks to the electron not as something with a huge size, but a much shorter one, including the period. Relativity tells you that the Lorentz contraction is by a factor of gamma. Gamma is the usual relativistic factor, which is 1 divided by the square root of 1 minus v square over c square, or, if you will, the energy of the electron divided by the rest energy. Now, if you're taking a typical relativistic electron, then you can have a value of gamma, which is going to be from a few thousand to 10,000, even more. So we are not talking about a small effect. This is a big effect. You are shrinking by a factor of several thousand the period of the undulator. We are going in the right direction, folks. And even more so, because actually this is not all, okay? Albert Einstein is giving us two different things to do. This is one. But then let's look at the second one, because L over gamma is not the wavelength in the laboratory. It is the wavelength in the reference frame of the electron. But this is not the place where we are using the X-rays. The place where we are using the X-rays is in the laboratory, where the electron is a moving source. This means that the radiation is being to be subject to another effect, which is the Doppler effect. Now, we know Doppler effect from everyday life. If you go to a train station and there is a train coming at full speed, then you can see that the noise goes like, "Ew." I hope you got that. Let me repeat. "Ew." It means it goes as the train approaches us to high frequencies and therefore to small wavelengths. Now, the same thing is happening for radiation, for electromagnetic radiation, but in that case, the phenomenon is strictly relativistic. And so what you are getting is a new factor, which is a factor of 2 gamma, okay? Altogether, this double effect of relativity is taking the wavelength from the period of the undulator, decreases by a factor of gamma because of the Lorentz contraction, by a factor of 2 gamma because of the Doppler effect. Altogether is 2 gamma square. This is what you see in the laboratory. If you plug some numbers, you find that you start from a 1 centimeter period and you are getting into X-rays. And now we are indeed in business. So all you do in synchrotron radiation and free electron lasers is a combination of relativistic effect, relativistic phenomena that is bringing you to the X-ray range. And so if you want to build a source using relativity, you need an accelerator to give you electrons of high speed. There they are. Then you need some kind of device. We proposed an ondulator, but there are others. And altogether, you're going to get radiation. So all this is very good. But the question is, okay, we demonstrated that by using relativity, you can emit X-rays. But we're not looking for a generic way to produce X-rays. We were looking for a way to produce excellent sorts of X-rays. Are we doing that? All right, before answering this question, we must make an agreement because we have to define what is a good source of X-rays, okay? In order to understand that, I'd like to propose an analogy. It is the comparison between fireplaces and flashlights. By and large, you realize that a flashlight is better than a fireplace, but let's see why. Okay, a fireplace can be very cozy, very romantic, but energetically speaking, it is a lousy deal. Okay, if you try, for example, to catch a rat, you realize that you're not going very far, and the reason is because the radiation coming from the fireplace comes from a huge area and goes in all the angles, and so it is not very effective in illuminating what you want to illuminate. A flashlight is much better, and that is because it's concentrating the radiation in a narrow angular range, and the radiation is coming from a small area. So we must find a way to express all these characteristics in order to define what is a good source. And this is leading us to the notion of brightness. So let's take a source. It is good to have a large flux, but it is not all. You also want to have a small area that is emitting, and you want to have a small solid angle. You put everything together, and you can see here that you can increase the brightness by either increasing the flux and or by decreasing their geometric parameters. So it is the combination of them that is giving you a good source, meaning a source of high brightness. So now that we agreed on the quality of the source, we can ask again the question, is relativity giving us, yes or not, a good source? Well, let's look at history. Now, don't worry about these units. They're very complicated and we're not going to use them. This is the range of time in which this business evolved. And we start from Röntgen and its discovery. And it's quite amazing that for many decades after the discovery of X-rays, the sources did not improve at all. And the medical sources are not very far from this. But then, bang, synchrotron radiation arrived, and this is what happened. There was a gigantic increase. Now, look carefully at the vertical scale. You're talking about a compressed logarithmic scale. And so here, during this period of time, we increased the quality of the sources by 22 orders of magnitude. If you're looking at computers, our colleagues in computer science brag about their improvements, but they all improved by 7 orders of magnitude. In X-rays, we've been doing much better than that. And so the answer is yes, relativity is not only allowing us to emit X-rays, but it's also giving us fantastic, fantastic sources. So of course, the question now is how is that relativity, in addition to giving us the short wavelengths, is also giving us this enormous brightness? And the answer is that this is because of 4 different factors. 2 of them are related to relativity and 2 are not. So let me start from the 2 that are not linked to relativity. The first one is the fact that in a conventional source, those we find in a medical cabinet, the electrons are linked to a solid, So if you emit too much flux, you just melt down the solid and you cannot handle a big power. Now, in an accelerator, the electrons are essentially free in a vacuum tube, and so there is not this problem. You can handle a much higher power. The second non-relativistic factor has to deal with the source size. Now, here, you must be careful not to make a naive mistake, because you can think that the source size actually is the cross-section of one electron, but it is not. And the reason is because in a typical accelerator, you don't get only one electron around, but you get many different electrons. So you get a situation like this, in which the size of the source is really the cross-section of the entire electron bunch. And now let me go to the last factors, or the four. The relativistic one, first of all, the fact that relativity increases tremendously the emitted power and also reduces the angular divergence. So let's start from the emitted power. And once again, it is very simple. This is a charge, an electron perhaps, that is accelerated in the transversal direction. And classical electromagnetism is telling us that the emission is proportional to the square of the acceleration. Now, this is from the point of view of the charge. Now we are adding relativity with the longitudinal motion. So we had to change the reference frame, and that's very simple, because the acceleration is a coordinate divided by the square of a time. The coordinate here is transverse, and so the longitudinal relativistic motion does not change that. What changes is the time, and the time changes by a factor of gamma. So the acceleration, which is 1 divided by t squared, changes by gamma square, and the power, which is gamma acceleration to the second power, goes like gamma 4. That is the energy, fourth power. That's fantastic, because we are talking about a gamma of a few thousand to the fourth power becomes a huge factor. So relativity is giving us an incredibly large flux, which causes some problems, because if you're not careful, it melts everything that is on the path. Now that's one aspect. There's another one here which is also interesting, that is, you also see in the denominator the mass. So the emission goes down like the fourth power of the mass, which means that we are never going to use the Large Hadron Collider as a source of synchrotron radiation, because hadrons, protons, are very heavy, and therefore they do not emit. Electrons emit. So that's why all the synchrotron sources are using electrons. So much about the power. And now the fourth factor is the angular collimation. Once again, if you are looking at things from the point of view of the electron, there is no angular collimation. It is the situation that you get with an oscillating charge in a radio antenna. And so it's going to be the cosine square law, which is a distribution with a broad angular range. But if you change, now you go to the laboratory in which the electron is moving, then you find that the emission shrinks to a very, very narrow cone. There is again an analogy in everyday life, which is not working very well right now because of the COVID pandemics. That is, if you had a match of the Italian national soccer team, and by chance the soccer team would win, which is not very much the case in these days, then the night after you find a lot of people going around town in cars and making a lot of noise. Now, if you are a physicist and you look at the phenomenon carefully, then you realize that the motion of the car is projecting ahead the noise, and so there is a sort of collimation. The same thing is happening for radiation, but once again, radiation means relativity, and this makes the phenomenon extreme. So let's see things from the relativistic point of view, and imagine that you have some radiation, a photon perhaps emitted in a transverse direction. Then you change the reference frame and you see the projection ahead. Keep in mind that the magnitude of the vector is constant because it's the speed of light. And so all you have to do is to have a rotation, and the rotation is bringing this angle, the forward angle, to a value which is about 1 over gamma, 1 over a few thousand. So you're talking about a very, very small angle, which means that indeed the electrons are behaving like super collimated flashlights. And so if you keep that in mind, you can play with these notions. I will not do that except for a couple of things, but you can go on, and take almost all the properties of synchrotron radiation and free electron lasers and understand them. So for example, let's go back at the ondulator. We've seen how the wavelength is determined by the characteristic of the ondulator, but now let's have a look again at what happens from the top, okay? That's the same picture I showed you before, only that this time I'm adding a small area detector. So this is the electron that ondulates, and let's follow. That's the torchlight, and you can see what happens. In case you did not notice that, let me repeat that, okay? See what happens. What happens is that because the ondulations are small, because the magnetic field is weak, then the torchlight, the flashlight, goes into the detector all the time, which means that you're going to get a pretty long signal pulse. And now you can exploit the Fourier theorem in mathematics, and you know that something which is short in time is going to be broad either in frequency or in wavelength. So in a couple of steps, you discovered that an ondulator is not only emitting X-ray wavelengths, but it emits a narrow band of X-ray wavelengths. You can go to another kind of emission device. This is a bending magnet. These are the dipole magnets that are around an accelerator to keep the electrons in a closed orbit. Once again, let's look at the top view, and let's see what happens. This is the electron, the cone, bang. Repeat, bang. Repeat again, in case somebody's sleeping. Okay, now you see what happens. That is, you don't get a long pulse, you get a short pulse. Short pulse, Fourier theorem, broad band, which is good in some cases, because if you want to select a specific wavelength, then you have a huge range to play with, and you can filter the wavelength you need. Now, before leaving this approach, let me propose a third kind of sources, what I call the wigglers. At first glance, a wiggler looks like an ondulator, but there is indeed a big difference, because in an ondulator you got a weak field and small ondulations. Here you get a strong field and therefore large ondulations. Same trick, let's follow. This is what happens. Once again, now in this case, you're not going to get one short pulse, you're not going to get a long pulse, you're going to get a series of short pulses. Fourier, this means a broad band. So to some extent, what you have here is a collection of bending magnets. And since it is a collection, you're getting more intensity than from a single bending magnet. So we already discovered a big fraction of the characteristics of synchrotron radiation source. But let me complete the picture by going to polarization. Polarization is something else that you want to have in order to have a good source. And we have been not touching polarization until now. Actually, it's very simple to understand. Take the three different points of view. That is, look at the accelerator, the storage ring, first from the top, second from the side, and third, a tilted view, a little bit of the plane of the ring. And let's see what happens to the electrons. The electrons are circulating. So from the top point of view, they are going in a circular path. Now, this is not very interesting because we learned about the flashlight effect. And so if you are getting at this angle from the top view, you get no intensity at all. So forget about that. But this one is more interesting because this is where the radiation is concentrated. And so the side view looks like a line, a straight line, and there is no mystery that the radiation is going to be linearly polarized. Here, you get elliptical polarization, which makes our friends chemists very happy, okay? Actually, this is not a good way to obtain elliptically polarized X-rays, and the reason is because, once again, there is the flashlight effect. So if you're getting off the plane or the ring, the intensity goes down. But there are other ways, so that is, you can get more complicated ondulators that are doing fancy things like spiral orbits and so on, and so you get good elliptical polarization. So we are almost at the end of the part dedicated to synchrotron radiation, and we are almost ready to go into the second and final part, which is X-ray free electron lasers. But there are a few things to still discover. First of all, let me make a summary. We discovered that we are emitting short wavelengths. We get linear on elliptical polarization. There is a time structure which is interesting, which is also very easy to understand, because if you take a storage ring, then you discover that the electrons are going around in bunches because they must be reaccelerated by special radio frequency cavities. And so what happens is that you get radiation anytime the bunch goes through a source like an undulator or a wiggler. So the time structure we are talking about is going to be a series of pulses, which is interesting because if you want to study a phenomenon that is time dependent, this gives you the start time, and then you can see what is the evolution of the system. Also, we discovered that there is a high flux, a small source area, a narrow angular spread, and altogether the things are giving you brightness. But there is one last and very important point, that is these two characteristics, small area and the narrow angular spread, are also giving you what is called coherence. So we must discover coherence. First of all, what is coherence? Well, let's keep things simple again, okay? I would like to define coherence as that property that makes it possible to observe wave-like phenomena. Now, you can understand that, first of all, by saying that we are surrounded continuously by waves like light or sound and so on, but we do not observe phenomena like diffraction or interference very often. Okay, one exception could be a soap bubble in which you can see the beautiful colors that are coming from wave-like properties. Why is this? Why are not we observing in everyday life this wave-like phenomena? And the answer is that a wave must also possess this property that we call coherence. In order to better understand this, you can use any kind of phenomenon of this class, like for example, the diffraction by a pinhole. Okay, this is a screen, this is a pinhole. And we start here from an extreme case in which you have a source with only one wavelength, and it is a point source that is a source with infinitely small size. Now, in this extreme case, you always get coherence, full coherence, that is, you always see a diffraction pattern. Things are changing when you start relaxing these conditions, and we'll discover two aspects in coherence. First of all, if instead of having a single wavelength, like here, you get a wavelength band, then you may discover that you no longer have a visible diffraction pattern. And this is what is called time coherence or longitudinal coherence. Second, if instead of having a point source, you have a source with a finite size, once again, you may discover there is no pattern anymore. And so you have a second kind of coherence, which is called spatial coherence. It's quite easy to understand what are the conditions for these two kinds of coherence. First of all, for longitudinal coherence, let's take the phenomenon. So if you take two different wavelengths, each wavelength is going to give you a different diffraction pattern. Then you add all the other wavelengths in the band, and altogether you may find that the superposition of the patterns is blurring everything out. So you get a blob, you don't see anything, okay? Now, if you're looking at the distance between two fringes, you find in elementary optics that this is the distance, which is given by the distance between the pinhole and the detector and the wavelength and the size of the pinhole. So if instead of having one single wavelength, you have a band of wavelength, this distance is going to be blurred by this. And so very simply, you don't see a pattern if the blurring is more than the distance, okay? And you plug the condition and you get very simply delta lambda over lambda smaller than 1. That's, by the way, why you see the colors of soap bubbles, okay? Because with your eyes, you take the radiation, the sunlight, and you find the eye is filtering, so the delta lambda is going to be the visible range, and this is almost automatically fulfilled for visible light, and so you can see the colors of soap bubbles. You can express the same condition by using what is called the coherence length, which is this quantity, and so you get time coherence. The coherence length is bigger than lambda. So much about time coherence. Okay, and second about spatial coherence. I'm not going to go into the details here, but once again, you can imagine that each point of the source is giving you a different pattern, but the combination may give you a blob. So if you work out the conditions once again, you can find very simply that the condition to still see a pattern is this one, that is the size of the pinhole much smaller than this combination of parameters. Now you can look at the same condition in a slightly different way, which is also quite interesting. Okay, it is suppose that the source, as is shown here, is emitting over a solid angle omega. Now you realize that most of the radiation is not participating to diffraction because only the portion that goes to the pinhole is giving you diffraction. And so the active radiation is a fraction of the total, the fraction being essentially the ratio of the two solid angles, and this giving you this one here after you plug the condition. So you get to this parameter, which is called the coherent power factor, and you can express the condition for spatial coherence by saying that a source has this kind of coherence if it has a large coherent power factor. So these are the generic definition of coherence. Now let's go to X-rays and synchrotron radiation. So what is the situation? That's the summary. First of all, we need a large coherence length, and second, you need a large coherent power factor. You look at these two parameters, and there is something that catches your attention. In both cases, you have a lambda square, which means what is easy for large wavelengths becomes beastly difficult if you go to short wavelengths. That is why you had in optics, in visible optics, this kind of phenomena for centuries, but in X-rays, we discovered them only pretty recently, and it was a good discovery, okay? So this is the first point. The second point is that if you go back to the definition of brightness, you realize that the same geometric parameters that give you a high brightness also give you a high coherent power factor that is large spatial coherence. So we got a bonus because we've been struggling for decades to improve the brightness by improving the geometry, and in the end we discovered that also got a spatial coherence. Since we have not been thinking about coherence for a long period of time, the X-ray scientists did not know very much about these aspects, but then all of a sudden we found that this source was not only good because it was intense and so on, but also because of that coherence. And now there are a number of techniques that are using coherence. Okay, I'm trying to keep track of the time because of the delay. I will try to shorten as much as possible. But we now had to go into the second part of my presentation, the last part, which is about lasers, okay? Because in our discovery until now, we found that a synchrotron radiation source has properties that are very much reminiscent of a laser. The high power, small size, collimation, coherence, and so on. So there is a legitimate question: are we getting a laser? And the answer is no. Okay, this is not a laser because the emission mechanism is different. It's not that of a laser. However, the novelty now in recent years is that we got a second class of sources which are absolutely fantastic, and these are the X-ray free electron lasers, or X-FELs. Just to give you an idea what we are talking about, this is an airplane view of the European X-FEL in Hamburg, and you better believe that it is a big machine. A similar one is in Stanford. There are a few others that are a little bit smaller, but in general, talking about machines of a certain size. And so the mechanism here is not exactly that of synchrotron radiation, it's a different one, and it is not exactly like a laser, but it has some properties of a laser. And so I would like to discover them very briefly, hopefully keeping the things again simple. All right, this is the general scheme of an X-FEL. You need an accelerator, of course, to get relativistic electrons. And in this case, we are using a linear accelerator and not a circular accelerator, a LINAC. Then we need a wiggler, and the wiggler must be very long, okay? And with certain conditions, you're getting a laser-like X-ray beam here, which can give you a lot of new opportunities in science and technology. Now, you know that in a laser, you have an optical amplification in order to enhance the intensity of the waves. So do you get optical amplification in this case? Yes, and it is very much like, excuse me, Giorgio, what is called in the US a Genoa salami, okay? Which is, I think, totally inappropriate. The optical amplification mechanism of an X-FEL is very much like a Genoa salami, okay? And let's see at what's going on. Here you have a bunch of electrons. In synchrotron radiation, we have been looking at single electrons. Now we are looking at the collection of electrons that are traveling together. Now the electrons enter the long wiggler, and there is one electron at random that will start emitting a wave. And then so from this point on, the electrons of the wave are traveling together, and there is something funny that is happening. That is, all suddenly, because of this interaction, you see that the electrons are no longer homogeneous, but they start reshaping their positions and getting a configuration which is like the slices of an Italian salami with a period which equals the wavelength. Okay, now this phenomenon, the micro-bunching, goes on and on and on. And when you get to the end of the ondulator or the wiggler, you find that the micro-bunching is now complete. So the electrons are confined to very narrow slices. Is this important? Yes, it is, because now if you're looking at how the electrons are emitting, then you find this. You can see that all the emission is coordinated. It's all in phase, and therefore, because of the reshaping of the electron bunch, you're getting a tremendous increase in intensity. That is, you have an amplification of the initial wave. So that is the basic mechanism. Only that in order to really understand what's going on, we need to discover why the interaction between the wave and the electrons are giving you the micro-bunching. So let's see, there are two ingredients here. The first ingredient will be the wave with its magnetic field, the B field of the wave. The second ingredient will be the oscillation of the electrons that is caused by the wiggler. So because of the oscillation, the electrons are going to have a transverse velocity, here it is, and the transverse velocity will oscillate, okay? Now we put together these two ingredients, the magnetic field and the transverse velocity. Velocity plus magnetic field equals Lorentz force. So we are going to get a Lorentz force. The Lorentz force is pushing the electrons towards a wave node where you have no field anymore, and so there is no Lorentz force. Now that's for one of the electrons, but let's repeat that for a few other electrons. You can see this one here and these others, and you realize that the Lorentz forces are going in the right direction. That is, they are pushing the electrons into these pockets, the slices or the micro bunches. And actually, they do that with every other node of the wave. And so the periodicity is going to be one wavelength. All right, this is the mechanism. Now, I like to make a small note that is, if there are people that are already familiar with X-fields, they may object at this point that actually there are not the Lorentz forces that are causing this phenomenon, but they are what is called the ponderomotive forces, which is a very complicated name for a very simple thing. All right, that's true. However, some time ago, Primoz Rebernik and myself, we demonstrated that actually they are the same thing. That is, formally speaking, the ponderomotive forces are giving you the same effect as the Lorentz forces. So you can use the Lorentz forces and simplify things as I have done here. All right, so now we have all the ingredients for the salami mechanism. And what's going on then is that you get a progressive increase in the intensity of these initially spontaneously emitted waves, which is called a self-amplified, self-amplified spontaneous emission. And so if you take a log of the wave intensity and you plot it against the distance, you'll see that there is some initial microbunching, but then you get into a situation of exponential increase. This is not going on forever. At a certain point, it saturates. So to complete our picture, we must answer the question, why do we have the exponential increase and why do we have the saturation? Now, for the exponential increase of the intensity, once again, is very simple. Take the four ingredients, that is the intensity of the wave, the electric field of the wave, and don't forget that the intensity is proportional to the square of the electric field as it is proportional to the square of the magnetic field. So the electric field and the magnetic field are proportional to the square root of the intensity. And then you get the transverse velocity. Then you ask, what is the transfer rate of energy from the electrons to the wave that is giving you the increase in the intensity? And you can realize very easily that is given by two factors. The first one is the transfer rate for a single electron. But then we also have the fact that the microbunching is contributing to this increase in intensity. So you have the two factors. The first one we learned is going to be, the second one we learned is going to be proportional to the microbunching forces, which is Vt multiplied by the magnetic field of the wave. The first one is going to be the work done by the wave. The magnetic field does not do any work, so it's the electric field, and the power is going to be given by the product of the electric field by the transverse velocity. So altogether, you get something which is proportional to these two fields, which is square root of I equals I. And so you get a simple differential equation, di over dt proportional to I, which gives you the exponential increase. Exponential increase with respect to time, but also with respect to the distance, which is the velocity multiplied by the time. So final question is, why is all this saturating? Well, don't forget that in order to get transfer of energy from the electron to the wave, the electric field of the wave must do work, and it must be negative work, so it transfers the energy from the electron to the wave, not the other way around, which would be a disaster. However, this is the initial condition. The electron loses energy because it transfers the energy to the wave, and so because of this, it starts slowing down. Eventually, the condition is reversed. You can see here that we go from this condition to this condition, which means that now we are in the disaster situation in which the wave is giving energy to the electron, and so the amplification saturates and no longer goes ahead. So we have the saturation. All right, we are in business. We have an X-ray laser, folks, and furthermore, it is a fantastic laser, but you may have a question, okay? Why, if you're taking a generic Wiggler undulator in a generic source of synchrotron radiation, we are not getting a laser, you're not getting an X-FEL? Well, the answer is that in order to get an X-ray free electron laser, there are some special requirements that you do not find for normal Wigglers or undulators. First of all, let's consider what's going on for a standard laser. And you know that in a standard laser, you have what is called an optical cavity, which is a combination of two mirrors that increase the total path and therefore the amplification. Can you do that with an X-FEL? The answer is no, because there are no mirrors for X-rays. X-rays are not reflected, so you can forget about building an optical cavity. And so now the conditions are stringent because you need to have enough amplification in order to get laser action in only one pass. And this requires a very special electron beam, electron bunch, which must be very small. So you must have a small cross section, which is good because it increases the brightness, and also a very small length, which is also good because the length divided by the velocity is giving you the duration of the pulse from the X-FEL, which is going to be in the range of femtosecond, and actually quite recently went below 1 femtosecond. Now, this means that you can use this kind of pulses in order to study all sorts of things that are happening on the femtosecond scale. And there is a lot of, all the fast chemical reactions and many other phenomena are in that range, the explosions. And so that becomes a very interesting kind of tool. And we'll see a little more in a couple of minutes. Okay. Now, let's look at the other characteristics. First of all, because of this fantastic geometry, we do get a very high spatial coherence, as it was demonstrated, for example, by the Fermi free electron laser in Trieste. Time coherence is problematic. It is problematic because we have seen that what is amplified are waves that are randomly emitted when the electrons are entering the Wiggler. And so this means that since this is a stochastic process, the shape of the pulses changes from pulse to pulse. And this is not good for time coherence. For example, if you want to use these pulses as a starting time for a phenomenon, you don't get a good starting time. How can you solve the problem? The problem can be solved by using what is called seeding. That is, instead of amplifying these randomly emitted initial waves, you are getting something with a good shape coming from an external source. And this was realized pretty recently. So that's the difference between the self-amplified spontaneous emission, which amplifies waves that are emitted by the electrons themselves, that it is, and seeding, in which case you get an external source, you shoot a wave, and this wave that gets amplified. And you can see here the demonstration that this is actually happening. Now, I have one final question before leaving. The final question is, now in this way, we are creating a monster, okay? Because here we are concentrating in a pulse that is only 1 femtosecond, with a very tiny volume, a power which is given by the 4 power of gamma, which is several gigawatts. Okay, that's a tremendous power. Actually, we have never seen anything like that in nature. Okay, it's the biggest concentration of electromagnetic radiation you can imagine since the Big Bang. Okay, now, all right, but can we handle this power? Can we do something about it? That's a bit of a problem, because if you are taking a molecule or a nanoparticle, this is what's happening. And a politician may come to you and say, all right, you have been spending a lot of money in order to destroy in a fancy way very small things. What is all about here? Okay, well, the secret is this word femtoseconds, because the femtoseconds can be short enough to catch up with the explosion. The explosion is lower. And so you can imagine to take these products and then go back in time and reconstruct what happened or was present in the beginning. We've been doing that. There are examples right now for nanoparticles, but of course the big dream is to go for molecules, okay? Instead of building crystals and try to find new pharmaceutical products by having to build a lot of crystals of proteins or biological molecules, to be able to do this one shot at a time and then simplify the entire process. It is half a dream in a sense that it's been realized for some scales, but I still hope it is going to be a realized dream in the future. That's it. That's all, folks. And so I'd like to thank, first of all, the people who made their results available to me. Primoz Rebernik, theory, Maya Kiskino, Yuquan Wu for experiments, the Institute for the invitation. But also I like to inject a little bit of optimism by saying that no matter how miserable we feel in these days because the COVID and so on, we should never forget that at least in X-ray business, we never had something as bright as this period of time. Thank you very much.
Thank you, Giorgio. Looking at the questions as they come, for the sake of time, I'll start reading already the first question, if you don't mind. So the first question is, what about the development of high-performance 3 giga-electrovolt SR facilities? What are the main advantages expected for these new machines?
Okay, in the entire history, which is pretty recent, of X-ray, free electron lasers, and standard synchrotron sources, you find the complementarity. Okay, that is, you are never going to use an X-FEL for something you can do with a synchrotron radiation source, and vice versa. Now, what has been happening in recent years, which I did not have the time to mention, is that people have been working very hard. In particular, I like to mention the European Synchrotron Radiation Facility, directed by Francesco Sette, and they developed a number of modifications of the machines, so they push the brightness to the absolute limit. Which is what is called the diffraction limit. And so now we have in parallel sources that are pulsed with extremely high peak power and sources that also gives you a very high average brightness. Both have very good applications, and I would be really it will be really impossible for me to make a ranking. Both are important and both should be developed.
I'm waiting for more questions. The live stream, I think, has a certain delay, so maybe they're coming. Oh, yeah, there's another question. Does a seeded FEL need a laser radiation for seeding? If so, can a seeded FEL emit in the hard X-ray regime? The paper you cited is about Fermi, so rather far UV FEL.
That's a very, very good question, because in fact, the production of the seeding poles is one of the major problem or the major problem in the seeding process, okay? Because we develop a free electron laser for X-rays because we do not have normal X-ray free electron laser. Now, what they've been doing in Fermi is to take a laser in the VUV and then use a technique which is called frequency multiplication that can increase the frequency and therefore the photon energy, but to some extent, okay? You can go to the far UV, but you cannot go to hard X-rays that way. And so you need to do something else in order to go to hard X-rays. And there are several possible schemes, okay, that is, you can imagine to have a separate source of synchrotron radiation or something like this with a number of devices to shape. Now, another possibility is that you can take the radiation from a SASI free electron laser, and then this is the first stage, okay? And then you filter this radiation. You need a monochromator to do that, so that you are narrowing the bandwidth, and that means that you are cleaning up the shape of the pulse, and then you use that for seeding. So there are solutions. They are invariantly very difficult, but there is a lot of progress going on.
I'm still waiting to see whether there's any further question. Giorgio, in the meantime, a very naive question from a non-expert, as you know. So the question I have, you mentioned this possibility of looking at chemical bonds, and in practice, what are the type of applications that have been explored over the years?
Okay, would you give me a couple of hours?
No, very quickly.
No, the reason is because actually there is a huge variety of application. I mean, the X-rays are the first ingredient, and then you can invent many different ways to do that. Let me just mention a few examples. When all this business started, it was primarily optics. Okay, that is relativity, absorption, and stuff like that. And that also gives you information about chemical bonds, because if you're going to from visible radiation, which you have the energies of valence electrons, and you go to X-rays, you also have valence electrons, but then you start picking up core levels. Okay, core levels do not participate in chemical bonds, but they are affected by chemical bonds because the charge redistribution of a chemical bond is changing the characteristics of a core level, okay? And so with optics, optical experiments, you can learn a little bit, okay? Then there was another very important technique that still is one of the main streams of this field, which is photoemission. Now in photoemission, what you do is you say, well, I would like to study the electrons in chemical bonds, but the electrons in chemical bonds are inside the solid, and so I cannot reach them. Okay, one way to solve the problem is to bombard them with X-rays, so they are shooting up in energy and they can leave the solid, keeping track of the initial characteristics. Okay, so now you can catch them in vacuum and retrieve the initial characteristics. So this is the basics of photoemission. Now there is a huge variety of photoemission with fantastic progress. For example, people are able to do photoemission microscopy on the scale of a fraction of a nanometer. Okay, so they are looking directly not only at the shape but also at the energy characteristics of very tiny things. Okay, now there is a big arsenal in imaging techniques, okay, because with coherence you can go out of simple absorption imaging to phase coherent imaging, and there once again there are all sorts of possibilities that also give you the information on chemical bonds. And I'll stop here because otherwise.
Thank you. There's another question in the meantime. At the end of the acceleration in FEL, the electron bunch is done, but could one use the electron bunch for electron microscopy or electron diffraction applications?
it would be a very complicated way to do that. You're better off in buying an electron gun. Because it is true that in principle you can get these electrons, but the machinery around is so complicated that it would be really asking for trouble. Now, one thing that you can do actually is to recover the energy of the electrons and inject it back into the system. Because the big problem with X-ray free electron lasers is that they are using a lot of power. Okay, and so if you can recover some of the power, that's good, because the cost of an experiment actually is not the cost of personnel or the cost of the machine, it's the cost of the power. Okay, so that would be probably a more sensible way to recover.
And there's another question that sounds interesting, at least to me. What are the perspectives for the application of the X-FEL technology in structural biology after the explosion of the single particle cryo-EM approach?
That is the dream I was talking about. Okay, let me elaborate on that a little bit. Okay, now the need to prepare crystals in order to solve structures, okay, is a big impediment in the progress in structural biology. And the reason is that basically not all the molecules like to form crystals, and there is a sort of bias that discriminates against the membrane proteins. So quite naturally, people that are in the business of solving macromolecules, they tend to favor things that are crystallizing. Now, nature can go in a different way, and the technological needs can also go in a different way. Okay, so there is so much you can do with crystallography, also because it's sort of biasing the entire field. Now, the possibility with a free electron laser is that you shoot a single molecule, you get an explosion, you see the results of the explosion, but then you go back in time. In order to do that, you must have, of course, software and so on and so forth, but also you must have a situation in which the explosion takes place over times that are long with respect to the pulse, because if the pulse is too long, then there is no possibility. Okay, and that is has been still is to some extent an open question, because before going into this kind of business, we did not know very much about this kind of explosions. We never had this concentration of power in such a small volume, and so in part we are learning now about the times of the explosions and so on, and we are making progress. Now, it all depends on, in the end, how much we can do given the situation. Okay, the free electron laser are getting shorter pulses. The modernization of explosion is becoming better. There are examples of structures solved with this technique, but it's not yet a standard technique. You must also keep in mind that there are other techniques in electron microscopy and so on. So this is a parallel effort. As it happens in many fields of science, I believe that this is not a horse race. It is more like a collective effort. In the end, in a few years, we are going to have a fantastic collection of new instruments that are making it will make it possible for structural biology to change radically.
Giorgio, I guess one last question, if you have a few more minutes. Can you compare laser-induced femtosecond X-ray generation with, I guess, there's a typo here, with tabletop, I guess, versus a huge synchrotron. So I guess it's comparison between the smaller and the larger.
Yes. Getting a small or tabletop X-ray source has been a dream during all the history of synchrotron radiation. But up until now, we got half results. We did not get a smashing success. And let me just give you an example. There is a class of synchrotron radiation sources which is called the Compton backscattering, okay, which can be squeezed to a table and gives you decent a decent source, but not a source of very high spatial coherence or very high brightness. Now, of course, that's important because you can have a trade-off in which you say, all right, I mean, I can have something that is not as good as a big synchrotron, but it is still giving us a lot for a reasonable amount of money and so on. Okay, so I think that these efforts are important and should be continued. There is a basic problem that is an accelerator becomes quote unquote nervous if it is small, okay, because all the instabilities and so on are complicated, which means that you need a very good accelerator team in order to operate, okay, and this is sort of countering the idea of going to a small source, for example, to put it in a hospital, because the hospital, the last thing they want to have is a machine that is nervous and only works when it likes, okay, or when there is a good operator. Okay, so it's a trade-off, and but quite frankly, the progress has been slower than we hoped a few decades ago.
Okay, Giorgio, I think there's no more question, but also I think we kind of at the end with the time slot. So I would like to thank you again for the talk. Indeed, it was, as you promised, very exciting and very colorful. And I mean, explain something difficult, and must say that I got the message, although, as I said, I'm not an expert in the field, but it's nice to know. So I'm very grateful for your time. I guess you'll be taking a virtual applause. There's no way across the connection to do that, but I'm pretty sure all the other participants were very happy. Thank you again.
Thank you.